A cross-encoder is not always the better re-ranker. LambdaMART, features, labels, and latency can change which second stage actually wins. You'll learn how the pieces fit into a workflow that scores passages with a cross-encoder and decides when LambdaMART re-ranking stays off stage. I'm Professor Pi, teaching search and IR with simple Python. Search systems need two things: speed and judgment. The first pass finds a few candidates fast. The second pass decides which of those candidates really answers the query. People reach for LambdaMART when they have handcrafted signals that correlate with relevance. They reach for a cross-encoder when interactions between query and document text look decisive. Success means we get better top results without blowing latency budgets. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We start by showing the baseline ranking, so we can see what actually went wrong and why a re-ranker might be needed. This snippet surfaces the lexical baseline ranking we start from. Engineers often trust the first stage score until it hides how relevance labels actually stack up. The list in docs captures each candidate as an ID, its explanation text, 3 handmade features, the original BM25 score, and the label we care about. Baseline order simply sorts by that base score, which mirrors a fast BM25 or dense retriever pass. Because our toy labels say D3 is truly best, yet BM25 still prefers D1. The misalignment is visible, but still grounded in real feature values. The printed line highlights the wrong winner, so we have motivation to fix it, and it makes the gap between a fast scorer and true relevance concrete for the rest of the demo. We need numeric features and grouped labels next, so a tree ranker can learn pairwise priorities from a query perspective. This example turns those hand-scored documents into dense features and labels for LambdaMART. Real re-rankers fail when feature tensors and judgments drift apart. So X stitches together signal strafe and the base BM25 number for every doc. Y captures the graded relevance labels and group notes that all 3 rows belong to one query, mirroring the grouped arrays LightGBM expects. The compact feature names list makes it obvious which heuristics we are feeding into the tree. With everything cast to deterministic NumPy arrays, we can share the structures across later snippets without copy-pasting. The print shows the group size and average label, so we can sanity check the query mix before training and avoid a silent data mismatch when the model learns. With features ready, we can train a LambdaMART ranker and see if a tree-based signal flips the wrong winner. This code trains LightGBM's LambdaMART on the toy query level data and applies it. Production rankers fall apart when we ignore how tree parameters change pairwise gradients. So the LGBM ranker block spells out the lambda rank objective, NDCG metric, and a cautious learning rate. Group passes the single query boundary array, so LightGBM optimizes the items together, instead of treating them as independent rows. After fitting, LambdaMART scores gives 1 score per doc, while NP-argmach surfaces which candidate the trees now like. LM top doc and LM top score make it easy to inspect the winning ID alongside its score. The printed values confirm that LambdaMART flips the lead to D3, matching the human label and justifying the extra training work when features capture the right signals. LambdaMART helped, but sometimes language models see subtleties that heuristics miss. Next, we run a heavy cross-encoder for a direct comparison. This snippet runs the BAAI bge-reranker-base cross-encoder over the same candidates. Cross-encoders stumble when we forget to form query document pairs. so pair inputs lays out the tuples straight from docs. Cross-Encoder loads the published BGE-reranker with a friendly max length cap that balances context coverage against latency. Predict streams each pair through the transformer, so cross scores holds a float per document instead of reusable embeddings. np.argmax then finds the highest reranker score, and cross-top-doc keeps the metadata ready for logging. The printed line lets us see BGE push D3 to the top, illustrating how a heavier reranker can catch nuance that LambdaMART may miss when features are sparse. But this comes at an increase in per-query inference time. Now, we want a fair comparison and a single metric to decide which second stage wins for our toy query. This code compares the re-ranking outputs with an NDCG check, so the winner is obvious. Choosing a re-ranker blindly is risky because different objectives inflate metrics differently, so NDCG score gives us a common yardstick. TrueRel reshapes the graded labels, and each score array gets reshaped once so the downstream calls stay tidy. The NDCGS dictionary captures results for BM25, LambdaMART, and CrossEncoder, so we can compare accuracy and wiring cost in one place. Max selects whichever method currently wins, but you could tie-break with latency numbers gathered elsewhere if needed. The print highlights the best method and its NDCG at 3, making the trade-off explicit before you scale the pipeline. If you map this toy flow to production, the BM25 pass becomes your candidate retriever. The feature builder runs where logs and signals live. LambdaMART trains on historical judgments, and the CrossEncoder runs on a GPU-backed service for a strict latency budget. LambdaMART shines when your handcrafted features actually predict relevance. It will flip winners correctly when those signals are present. A CrossEncoder wins when the text interactions matter and you can afford higher latency. One caveat: models can agree on winners for the wrong reasons, so always measure with a common metric and log latency. Next step: tune the BM25 K1 and B parameters on your baseline retriever and reevaluate NDCG at 3 to see how the candidate set quality changes before you add a heavy re-ranker. If practical IR help matters, subscribe and watch the IR videos.